So now we will look at some easier ways of dealing with how to get the threads to do different stuff by means of work sharing constructs. So what we've seen so far is a way to control the parallelism by means of something called SPMD, which stands for Single Program Multiple Data. That is, each thread redundantly executes the same code, and you split up the pathway through the code using knowing the number of threads that you have and the thread ID of each thread. But there are better ways to split up a code and make them do different things, for different thread do different things, called work sharing construct. And in OpenMP we have ways to deal with loops, sections, which is functional distribution, and then single construct, which sounds funny because this is a way to get one thread to do a particular thing, and the task construct, which we'll talk about later on. The loop construct, which is by far the most commonly used way to get parallelism in C code. So the loop work sharing construct its name is Pragma OMP 4. In Fortran it's called do, because a for loop in Fortran is called a do loop. So the for work sharing construct works on the next statement has to be a for loop like this one. The iteration variable I will be automatically made private to each thread, and then the iterations of this for loop will be divided so that each thread gets a portion of the for loop to execute. And you as a programmer will have to make sure that the loop body, the iterations body, can be executed in any order, and in particular in parallel. So in this case, if we have, for instance, two threads, when you come to the for loop, thread 0, because they are numbered from 0 and upwards, thread 0 will execute iteration 0 to n over 2 minus 1, and thread 1 will execute iterations n over 2 to n minus 1. Okay? So here is a motivating example why this is very useful. Let's say we have this sequential code. You can write it in one line. Vector addition. You take two vectors, A and B, and then you want to element-wise add them together and put the result in the A vector. If you have a SPMD style of programming, this is what you get. You have to figure out your thread identity. You have to figure out how many threads you have. You have to calculate the starting index for each thread, and you take then the thread ID times the number of iterations, divide by the total number of threads, and then you get a start ID for one thread, and then you get the end ID calculated by this. And then you have to do some extra code to figure out if n is not evenly divisible by number of threads, and then you have the loop. Each thread will then execute this code here, from I start to I end. It works. Not very pretty. You sort of dwarf the real code behind the management code here. With the for work sharing construct, all you need to do is to put the Pragma OMP4 just before the for loop, and then the compiler will generate basically this code for you, but you don't need to see it as a programmer. If you want to make it even more shorter, you can just write like this: Pragma OMP parallel 4 on the same line. So you can have parallel and 4 on the same line, and that works just as well as having two lines here. So the different iterations may be scheduled in different ways, because it might be the case that the different iterations have different computational demands. So the default is most often static, where you take the number of iterations divided by the number of threads as the number of the chunks to hand out. But you can specify a smaller chunk size if you like. If the number of the iteration execution time is highly sort of dynamic, so you don't know how long they take, then it might be useful to use one of the dynamic schedules, the dynamic or guided. Also, these can be specified with a chunk size, handing out 10 iterations, 100 iterations, 500, whatever you have, which is suitable for your particular needs. The guided schedule is a way sort of mix between static and schedule. It tries to minimize the overhead. There is some overhead of doing dynamic scheduling, because at every time you have executed a chunk, you have to ask the runtime system for a new chunk, and then the runtime system will have to lock data structures and things like that to figure out which chunk to give next to this particular thread and so on. There is a central synchronization point in doing that. You would like to avoid that as much as possible. With the guided schedule, you will start with big chunks with low overhead. There is no overhead. There is the same low overhead as in static when you execute a chunk. But then when you come to the runtime system and you gradually come to the end of the iteration, the loop, you gradually shrink the chunk size until you reach the specified chunk size here. There is finally a way to specify that the schedule to be used is specified in runtime, and then you have an environment variable where you basically specify one of these choices here. So you should use static when the iterations execution time are predetermined and predictable by the program. It's the least amount of work at runtime. It's all being done at compile time. You should use dynamic when you have unpredictable, highly variable work per iteration. And you should use guided if dynamic seems to be too much overhead, because that will reduce scheduling overhead slightly. Dynamic has most work at runtime, complex scheduling logic, and static has least work at runtime. Use that whenever you can. And as I mentioned before, having a parallel region and then followed by a for loop immediately can be written in a shortcut like this. Completely equivalent ways of expressing the same thing. So, as this is so important way of using OpenMP, it's worthwhile to consider a little bit sort of the approach taken. First of all, you need to find the compute-intensive loads in your program. To do that, you use a profiler. So Profiler is a tool. There are many sort of open source profiling tools, and there are also tools that are proprietary. One good proprietary tool, which I can recommend, is the VTune profiler from Intel. It's possible to download a 30-day evaluation version of it for Windows or Linux. This is a very good one. I recommend to try it out. But there are free ones also. When you found a compute-intensive loop, you need to make the loop iterations independent, because OpenMP do not do that for you. The for loop has to have independent iterations. And then you place the appropriate OpenMP directive in test. So look at this example here. Assume that this is a compute-intensive loop, then this is not a. Then this loop has problem, because the iterations are not independent. You have a loop carried dependence on the variable j here, but you can transform it. You can, for instance, instead of doing j plus equal 2, you can calculate the j, and you can privatize it by declaring it inside, and you can calculate it like this way. And this is a typical example of how you can replace sort of communication or concurrency problems, replace them by computation that you do instead. And this is typically beneficial to do. And then the loop, it becomes parallel, and you can add the pragma and make it run in parallel. What about this case then? This is a very, very common case. You have combining several values into a single accumulation variable, AVE here. This is called a reduction. You reduce some values to a single scalar variable. So it's so common that there is a particular construct in OpenMP to deal with it. So this is a clause that you put to the for loop the work sharing construct. You can specify that the variable is a reduction variable. So in this case, the AVE variable is a reduction variable, and the operation you perform on it is plus. What happens now is that the compiler will create a local variable for each thread, and it will use that variable to accumulate each thread's result, and then at the end of the for loop it will combine all these values somehow into the single scalar variable. And this variable AVE must be a shared variable, but locally inside the loop it will be a private variable. So here we see some of the operations you can make on it. You can do plus, you can do multiplication, subtract, minimum and maximum, and in C you can also do bitwise and, bitwise or, bitwise exclusive or, logical and logical or. Now go back to the Pi program, the example, and parallelize it with the loop construct instead. And the goal is to minimize the number of changes made to the sequential program. In fact, the serial program, you need only add one single line of statement in OpenMP to make it run in parallel. Then if you go back to the code you downloaded, you found a code called matmul.c, and then you can play around with different scheduling. If you parallelize this code, and you can play around with different scheduling methods and see if you can optimize the program. Unfortunately, scheduling is sort of a craft business, so it can take some experiments to find out the best schedule for a particular loop.